Today on Macaulay Math, we're solving trigonometric equations. Intro. Okay, good day. I'm Professor Macaulay. This is Math 150, Pre-Calculus, Lesson 26 on solving trigonometric equations. Our goals for today. We are going to use standard algebra techniques to solve trigonometric equations. We're going to solve trigonometric equations of quadratic type. We're going to solve trigonometric equations involving multiple angles. And we're going to use inverse trigonometric functions to solve trigonometric equations. In this lesson, students will solve trigonometric equations. Since trigonometric functions are periodic, there may be many times when there are an infinite number of solutions to a given problem. Sometimes these solutions are limited to the solutions over the domain of the unit circle from 0 to 2 pi. You will have to read the problem to determine how many solutions are necessary and how to write a general solution if an infinite number of solutions are required. Let's get started. Okay, we still have the unit circle up here because I'm going to have to refer back to it a couple times during this lesson. But I want to get started by saying that trig functions are periodic, therefore they may have more than one solution. And I'm going to show that with a Desmos demonstration here by putting sine x as one function and a half as a second function. And so if I come over to Desmos, we can see that this periodic function, my sine curve, is going to repeat, and I have multiple solutions, multiple intersections where sine is equal to a half. Clearly at pi over 6 and 5 pi over 6, it is equal to a half. But if I scroll to the left and keep scrolling, you can see that I'm going to have multiple solutions over the entire real number line. If I talk about the solution as multiple values over the unit circle, remember when I say solve sine of x is equal to a half, that's literally asking me to find all of the angle measures where the y value on the unit circle is equal to a half. So if we refer back to the unit circle here, I'm looking for y values that are a half. At pi over 6, I've got a half, and at 5 pi over 6, I have 1/2. And we see back here in Desmos that the intersections happen at pi over 6 and at 5 pi over 6. So when they say the solution as a multiple of values on the unit circle, we go back up to the unit circle at pi over 6, and then if I go all the way back around, pi over 6 plus 2 pi, which will be equal to pi over 6 plus 12 pi over 6. 12 pi over 6 is equal to 2 pi. That'll give me 13 pi over 6. That'll be another solution to that problem. And you can see that that will be a solution if I come back to Desmos and I go sine 13 pi over 6. I again get a half. Similarly, with 5 pi over 6, if I go 5 pi over 6 and I add to that 2 pi, again, I'll go 5 pi over 6 plus 12 pi over 6. That'll be 17 pi over 6, which is another solution. So when you get to the practice work and they say solve versus finding all the solutions over an interval, let's do the easy one first. This asks me to find just the values of x that make this expression true from 0 to 2 pi. So using the unit circle, it is just these two values. We've already found them. So for that first one, it's just x is equal to pi over 6 and 5 pi over 6. Now when it says solve or find all of the solutions. Well, there's an infinite number of those solutions. I'm going to have my pi over 6, and then I'll add 2 pi to that to get 13 pi over 6. And then if I add another 12 pi over 6, that'll be 25 pi over 6, and it'll go on forever. So I need a way to generalize that. And the way that I'm going to do that is I am going to add multiples of 2 pi. So I will have x is equal to pi over 6 plus I need multiples of 2 pi. So there's my 2 pi, and I'm going to say multiples of that. I'm going to say times n. And then I will have the same thing for this. I'll have 5 pi over 6 plus 2 pi times n. And then I have to say what n is. Well, I just need it to be counting numbers. It just need to be 1, 2, 3, 4, 5, 6, and then the negative values as well. So I am just going to say where n is an element of the integers. Okay. Next, again, I'm giving you a toolbox to solve these functions. This is not an algorithm. You don't necessarily start with one. These are just some general guidelines. But first, substitution. Example, transforming an equation that has only one trig function in it is easier to solve. So if they ask you to solve an equation that has a sine and a cosine in it, see if you can find a simple trigonometric identity that changes that equation so that it only has sine or cosine in it. The second tool I'm going to suggest is simplify. And just as an example, an equation that has one term or one fraction is easier to solve than an equation with two. If you have a sum of two fractions, maybe condense that into a single fraction, and that'll make it easier. Use multiple angles. Example, solve the equation as if the multiple angle were just x, and then find the multiple angles. And what I mean by that is if inside the sine you have like 2 times x, solve it if it was just for x. And I have an example for that in a little bit. Property of the product of zeros. An example, set the equation equal to 0 and factor, and then find the 0 of each factor. And we've done that for polynomials earlier on in the semester. The example says functions in quadratic form. Find all the solutions over 0 to 2 pi. Now, for just a moment, I'm going to ask you to think of it as if it were 2y squared minus y minus 1 equal to 0. Now, this thing is easy to factor. It's 2 times y minus 1 times y plus 1. And then we'll use that property of product of zeros and set each of these equal to 0. So I'll get positive 1/2 and negative 1. I'm going to do the same principle with this expression, but instead of y's, I'm going to just use sine x. And so I will go 2 sine x minus 1, and then sine x plus 1 equals to 0. And then I will set each of those two expressions equal to 0. So it goes 2 sine x minus 1 equals to 0, and then sine x plus 1 equals to 0. Getting sine by itself, I get the sine of x is equal to 1/2, and I have the sine of x is equal to negative 1. And we've already solved this a couple times in this lesson, so the solutions to this one is pi over 6 and then 5 pi over 6. And then I can use what I know about the unit circle to figure this one out. Now, hopefully you're doing this in your head already, and just seeing that unit circle in the back of your head and saying that clearly the y value is negative 1 at 3 pi over 2. And those are the only values over this interval from 0 to 2 pi that make that equation true. All right, next example. It says find the solutions over 0 to 2 pi. Okay, so I have secant x, tangent x. And this one's difficult because clearly I have two different trig functions here. And I don't have a quick substitution to transform secant into tangent or tangent into secant. But I do know one of the Pythagorean identities that says that 1 plus tangent squared x is equal to secant squared x. If I subtract the tangent squared x and rewrite this as 1 equals secant squared x minus tangent squared x, I could substitute in a 1 for that. And so what I'll do is I will multiply both sides by the conjugate. And so if I go secant x plus tangent x times secant x minus tangent x equals to 1 times secant x minus tangent x, I will get secant squared x minus tangent squared x is equal to secant x minus tangent x. And I can do that substitution. This becomes 1 equals secant x minus tangent x. And I know that that does not look like I'm getting anywhere, but now I have two separate values that are both equal to 1. So I can set them equal to each other and say secant x plus tangent x is equal to secant x minus tangent x. And if I add tangent to both sides and subtract secant from both sides, I'll have 2 tangent x is equal to 0. If I divide both sides by 2, I'll get tangent x equals to 0. So tangent x is always equal to 0, so we'll save that. And go back to the original equation. So I have secant x plus tangent x is equal to 1. I can say secant x plus 0 is equal to 1. And so secant x is equal to 1. And so I have two different factors. I have this expression, I have this expression. Tangent x is equal to sine x over cosine x, which we know is now equal to 0. So where on the unit circle is sine x over cosine x equal to 0? So the only angle measure where this whole expression is going to be equal to 0 is when the angle measure for sine is equal to 0. And that is going to be at 0 as well as at pi. Now I also need to know where secant is equal to 1. So secant of x is equal, if you remember, to 1 over the cosine of x, and I need that to be equal to 1. Now the only way this fraction can be equal to 1 is when cosine is equal to 1. And cosine is equal to 1 only at 0. So these are my only two solutions for this problem. Next, it asks me to solve the equation. Cosine x times cosine x minus 1 is equal to 0. Now, this expression is easy to solve, but you'll notice there is no limitation of solve from 0 to 2 pi. So they want all of the solutions here. Now, let's start by just finding those solutions on the unit circle. So I need to know where cosine of x is equal to 0. And I need to know where cosine of x minus 1 is equal to 0. Now, cosine is equal to 0. That's pretty easy. Cosine is equal to 0 at pi over 2 and at 3 pi over 2. And if you need to check your unit circle, do that. But Hopefully by now you've got that unit circle memorized and these are easy solutions. Now I need to know from my other solutions where the cosine of x, if I add 1 to both sides, that'll give me the cosine of x is equal to 1. Now the cosine of x is equal to 1 only at 0. So these are the only solutions on the unit circle from 0 to 2 pi. So I need to find all of the solution, and to do that I am going to add those multiples of 2 pi to each of those terms. So all I need to do is just say x is equal to pi over 2 plus 2 pi n, 3 pi over 2 plus 2 pi n, and 0 plus 2 pi n, but we're too smart to write that as a final answer. So we'll just put 2 pi n, and then we'll say where n is an element of the integers. Next, solve over 0 to 2 pi. So I have 2 sine squared x plus 2 cosine x. Well, there is a Pythagorean identity that I can use to substitute cosine in for sine when sine is squared. And that is that first Pythagorean identity, sine squared x plus cosine squared x is equal to 1. And if I subtract cosine squared x from both sides, I'll have sine squared x is equal to 1 minus cosine squared x. That'll allow me to do a quick substitution. And say that this is 2 times 1 minus cosine squared x equal to 2 plus cosine x. And here I will distribute. That'll give me 2 minus 2 cosine squared x equals to 2 plus cosine x. And I want to set this equal to 0. And if you notice, I've got a 2 on both sides, so if I subtract 2 from both sides, those will cancel. And I want to keep everything positive, so I'm going to add this 2 cosine squared to both sides. That'll give me 2 cosine squared x plus cosine x is equal to 0. And here I will factor a cosine x. That'll give me cosine x times 2 cosine x plus 1 equal to 0. I will set each factor equal to 0. That'll give me cosine of x equals to 0 and 2 cosine x plus 1 equal to 0. On this interval from 0 to 2 pi, cosine is equal to 0 only at x equals pi over 2 and at 3 pi over 2. And then this one I got to solve for cosine x first. I'll go cosine x is equal to negative 1/2. And so cosine x is equal to negative 1/2 at only 2 places, and that would be at 2 pi over 3 and 4 pi over 3. And since those are the only possible solutions over that interval, we'll put a box around this and say we are done and move on. All right, last question. Here is a question that has a multiple angle. And a multiple angle is defined when we are multiplying an angle by some sort of scale factor. And so the way that I'm going to do this is I am going to solve as if it were sine of y is equal to negative square root of 3 over 2. So I'm going to say sine of y is equal to negative square root of 3 over 2. So what values of y make this expression true? Turns out that 4 pi over 3 and 5 pi over 3 give you negative square root of 3 over 2. And again, if you don't understand that, that's fine. Just check your unit circle. Now here's the thing. If it were just sine y, we'd be done. But it's not. We are actually solving for the sine of 2x. And what does this 2x do to our problem? Well, let's go to Desmos and look at it. Okay, so I have this set up. And right now, I only have f of x equals sine x and h of x equals negative square root of 3 over 2. I've made a function out of both of these sides. Now, you can see that I have a number of solutions. And the two solutions, 4 pi over 3 and 5 pi over 3, we've already found. But what does this 2x do? Well, it's a horizontal shrink by a factor of 1/2. And what that does is that means that there are more solutions than the ones that we already have. And you'll notice that they are not the solutions that we have. So how do I come up with the more solutions from 0 to 2 pi? In fact, there should be 4. Well, I'm going to do this. I'm going to say, all right, I am not solving for y. I'm actually solving for 2x equal to 4 pi over 3 and 5 pi over 3. And if I were to just solve for x, I would divide both sides by 2. That'll give me x is equal to, well, if I divide 4 pi over 3 by 2, I'll have 2 pi over 3. And if I divide 5 pi over 6 by 2, well, 2 doesn't go into 5 like 2 went into 4. So I actually have to divide the whole thing. It'll actually be 5 pi over 6. Now, if we go back to Desmos, we see 2 pi over 3, 5 pi over 6. But I also need 5 pi over 3 and 11 pi over 6. So how do I get those? Well, we do multiples of the unit circle up here until we get enough solutions. If I added 2 pi to 4 pi over 3, I would get 10 pi over 3. And then if I added 2 pi to 5 pi over 3, I would get 11 pi over 3. So if I did the same thing to those values, 10 pi over 3 divided by 2, I get 5 pi over 3. And then 11 pi over 3 divided by 2 will be 11 pi over 6. And notice, 11 pi over 6 is almost 2 pi. If I went up here and I did it again, let's say I added another 2 pi to the 10 pi over 3, that'll be another 6 pi over 3. That'd be 16 pi over 3. And if I divided 16 pi over 3, I would get 8 pi over 3. Now, 8 pi over 3 is clearly outside of this interval that we were given. So we would not use that, and we would mark this as our final answer. Okay, that's all I got for today, folks. So, Star Wars fun fact of the day. Blue milk appears in episode 2, Natalie Portman here, episode 4, Mark Hamill, and Rogue One. I don't know this actor's name. Well, that's all I got for today, folks. You have a great day. Goodbye.